Hi, everyone. Good afternoon. I have a question. How many of you are gamers? Wow, amazing. My friends. How many of you know The Last of Us? Either the series or the game. Cool. So in The Last of Us, those of you who don't know that, there is some fungus that takes over humans' brain and controls them. But this is not a new idea, right? We have it in The Walking Dead. We have a virus that does that, and we sometimes have ideas about aliens who do that. And it looks as if it's only in stories, right? In books, games, and movies. How many of you think there is such a thing in real life? Conspiracy theorists, nice. So you're right, actually. Nature. It's one of the highest regarded scientific journal. They found a parasite that makes mice lose fear of cats, which is problematic for the mice, very good for the cats. The thing is that this is what happens. Usually it doesn't end with a kiss, it ends with the mouse inside the cat. But our problem is that we also get this parasite, okay? And we get it by coming in contact with cats and also with, sorry, with animals that came in contact with cats. We sometimes eat these animals and we have this parasite. So the big question we need to ask ourselves is, do we think this is cute because we really think this is cute? Or are we being mind controlled by this parasite? So yeah, so I'm not gonna control your mind, but let's get back to games. We start from The Last of Us, which is a game. So why games? Okay, look at the warning, please, and yeah, disclaimer, whatever. I'll try to make this sound.
It says stay crouched and follow him, Scott. He's gonna wait. All right, we're gonna chase him down. Let's go, boys. Ah, get him off me. Nice, let's go. All right, I don't want to get, oh my God. Holy shit.
Okay, I'll stop here because it goes not so vegan friendly from now on. But in this short demonstration, you saw a player playing the game and swearing and really into the game. Okay, and this is possible because the game moves smoothly. If this player experienced lags, for instance, he would be swearing the developer, probably. And we don't want that to happen. So my talk is going to be how to make your users more happy and actually enjoy using your apps by learning from how game developers do that in their games. I'm Yonatan. I've actually been here last year, and I'm really thrilled to be here last year, and really thrilled to be here this year again. I'm a software architect at Vonage. I used to do a lot of stuff. I also been a neuroscientist. I didn't research this parasite, but I know a bit about the brain. I'm also a runner. I won a half marathon, and this is the next generation. I think he's running faster than I do nowadays. Okay, so who thinks design patterns are dead? Yes. Okay, cool. Nobody. Amazing. Because I heard that a lot. Actually, it's a Java conference, so you probably think design patterns are the only way to develop. But actually, design patterns are, you can use it, algorithms or solutions that were developed or formalized to solve something that happens a lot, okay? The iterator pattern, for instance, we use it all the time. But not many people know that some design patterns were meant to solve problems that arise from how the computer works and how we can abuse that to create performance issues. So We're going to see how we can interact with the CPU and make it run faster or not slow it down. We'll take a look how memory works and how design patterns interact with memory to avoid make it run slower. And we're going to also look at bandwidth. And a new thing, we're going to look at the climate crisis, how we as developers can contribute to slow it down or prevent it. So let's start with CPU. Okay. Our apps sometimes describe the world. We take some data and we present it to the users. Okay, in my line of work, I created a few real-time applications. I got data from multiple sensors and I had to present it in a humanly understandable way to the user. So let's take an example of an app that serves, okay, it's a made-up app, serves the veterinarian department in Washington, D.C. Okay, they attach a GPS chip to the cats and they follow them and they try to save the cats, make their lives better, and so on. So they connected, let's say, 50,000 cats to the system. And they want to use the system. It's using Cesium.js, which is a wonderful library. It's like Google Earth, only native for the web. But when the veterinarian wants to use the app, it's just stuck. Okay, the veterinarian presses the buttons and nothing works. And we need to find out why. And it's not a cat mind controlling the veterinarian, it's something else. So if you monitor the app, what you see is that half the time of the app just showing on screen is spent on scripting. So the CPU just works when nothing happens on screen. Okay? So we need to see what happens. So we dive deeper into the code. In this case, it's Cesium.js code, but it can be any other library or even your code. And first, we see there is something called render. So games are created with a rendering cycle. It means that every frame, the game checks what changed and creates the scene for this frame. So Cesium works the same. On every frame, it checks all the entities we have on the map and updates the view itself. But what we see here that there are two methods for the billboard and the label that take a lot of time to run. Okay, so we see that and we want to find out what happens. I won't go too much into the code, but what happened in Cesium is that the update function was called every time, even if this entity didn't update. Okay, so this is a classic case for a pattern called the dirty flag. And you probably used it several times. Maybe you didn't know it's called the dirty flag pattern. You probably called it just dirty or dirty flag or without the pattern. But we saw the problem. The problem is that we have some costly process that we repeat a lot of times, but we don't really need to if nothing changed. Okay? And the solution would be to flag this piece of data we don't need to process and just skip it every time we don't need to, sorry. So how does it look like? Let's say we have a socket connection and we get some cat update. So we get the cat from our list, we update the cat, and we said, okay, we got an update for the cat, so we set it's dirty to true. Cesium sees this dirty equals true. It says, okay, I need to update this entity. After it updates the entity, it changes dirty to false, and then the next time it skips it again. Okay, so until we get an update, we skip the entity, and we move from this way of the app to this. Okay, almost no time scripting, and we freed the CPU. So this is what the dirty flag pattern is about. Okay, it's about freeing up your CPU or your thread or however you want to call it. And as we said, the problem is that we have a costly process. We repeat it a lot, even though we don't need to. The solution, just process what changed and not what not everything, sorry. And we saw the algorithm. It's pretty easy. Set a flag. If it's true, process. If not, just skip it. So we talked about when to use. I can't stress enough the importance of monitoring, but do monitor your app to see if you really need that, and if that's the case. And more examples is in the JavaScript world, for instance, every framework uses the dirty flag pattern when in its change detection mechanism. So Angular, React, when something changes in the DOM, it flags this part of the DOM as changed, and then it processes it on the next change cycle. This is a link to the blog. You don't need to copy it. I'll just show in the last slide. I'll show a link to all the links that I share in my talk. But this whole process was described in this in the official Cesium blog. It helped me save my job at some point. Okay, let's get to memory. So who recognizes this game? Yeah? No, that's Star Control. Okay, that's the new version of Star Control. I actually bought the game because I used to play Orco and Masters as a kid. Yeah, I bought it mainly for nostalgia. But what you can see here, what I want you to look at is all the lasers and explosions and stuff like that. So anyone knows how it's called in gaming? Anyone heard of particles? Okay, so it's called particles, and I don't think I'll surprise you as people who come to a Java conference. Every particle is an instantiation of a class. Okay, so every laser beam is a class, the spaceships are a class, every explosion, or maybe even every part of the explosion is a class, but you can see that a lot of classes are instantiated and destroyed in pretty short time. And this is the problem we're going to talk about. So to get a baseline, let's see what allocation is really quick, because probably all of us know that. So we have a memory, and our memory looks like a big array. And we want to get some piece of data to store some data in it. So it finds a place to put our array. And then we want to push into this array, so it needs to allocate new place for the new array. So this process takes time, and we want this process to happen not when our user interacts with our app, or not when we're running animation or stuff like that. We want it to happen when the system is idle mostly. Anyone remembers that? Defrag, yeah, amazing. So this is defrag actually for hard drives. This is the newer version from 2000 something. But defrag solved the problem of fragmentation. And what happens in fragmentation? We allocate memory, okay, and then we get rid of something, and then we have a hole in memory, okay? And this causes the allocation process to take longer, because sometimes we don't have enough memory here to store cool things, so we need to search here. And sometimes all the memory is like fragmented, so during our customer's use of our app, it needs to do the defrag, and we don't want that to happen. So it's going to make everything worse. But the worst thing is garbage collection. Okay, garbage collection exists in most high-level languages. So unless you do C or C++, you're going to have garbage collection in your environment. This is how it works in V8 for JavaScript, but it's the same for like everything. Garbage collection is the process in which the language or whatever looks for the engine, looks for objects that are not referenced from our code, and then it clears it from memory. Okay, and here you can see an example of monitoring. This is on a Node.js server. there is a function called build array1, and you can see lots of instances of garbage collection during the function's run. And this makes our function runs longer. And we want our business logic to run faster, not take longer. What more you pay for cloud just for garbage collection. So we want to avoid that too. This is how it looks without garbage collection. So this is our business logic, and it runs smoothly. So this is a schematic view of how garbage collection works. So we have something running. It can be Java, JavaScript, Python, whatever. And then garbage collection kicks in because we cleared a lot of things from memory. And then our code continues. We don't want that to happen. Some would say we have threads to do that. So yeah, there are optimizations to run parts of the parts of garbage collection in different threads, but eventually you must have part of it running on your main thread, because otherwise you'll have race conditions. You'll delete something that you still need later, or stuff like that. That's bad. So we have allocation and allocation that takes time. We have fragmentation that makes it worse, and we have garbage collection. Okay, and game developers can't have them interfering user experience, and actually, why should we as application developers? Let's see an example in real life. Help. Let's see. Okay. Can you see? You don't need to see the buttons, you just need to see what's written in the console. So let's create and destroy. So we have some process that took around a second. Can you see the red writing? Let's do this. And if you create it with the solution, we see it takes around 10% of the time to run or something like that. It's not something one can ignore. So let's see what happens here. Okay, so the problem is, we said, is that we have a lot of create and destroy, like we saw with the particles. And our garbage collection kicks in and works during our functions, whatever the function, our processes. So the solution is to use an object pool. An object pool is practically an array that has a pre-instantiated object of the same class. And when we need a new one, we just ask it to get us one free. When we finish using it, we say, free this one, we don't need it anymore, and it just gets it into the pool of free objects to use. This way, we don't create anything, we don't delete anything, we just use it. So if we go back to our code, let's see. Performance. So I'll now show you a crash course on how to monitor or profile performance in JavaScript. Okay. So I'll start profiling, and I'll create with a pool, and then I'll create and destroy, and I'll stop. So this is the create with a pool. Let's see. Okay, and if I search for, let's say, minor garbage collection, I see 1, and major, I see nothing. Okay, so we can see this one. This is the just create and destroy without a pool. So we see 2 major garbage collection, and minor, we see 46. Okay, so this is very significant, and it slows down our app drastically, as we see in the measurement in the console. Okay, so we can have the same function running 200 milliseconds or 1 second. Okay, if you scale it in the cloud, you pay a lot. Okay, Okay, so when to use it? This is the object pool. So you use it when you have a lot of create and destroy processes. Okay, and you'd like to save on processing time. It actually takes time from your CPU by making it working on managing your memory. Another problem is that it happens in unexpected times. Okay, there are heuristics within the engine, either JVM or V8 or whatever, that handle the timing, and you don't want it to happen exactly when your users expect an answer or a response from the server. I spoke a bit about cloud costs. It can save you cloud costs. You saw the significant. Do the math. I don't know what scales you're dealing with, but it can become quite significant. The pros are pretty obvious. You improve performance. The cons are that you build a new mechanism. It's not your usual array. You need to learn how to work with it. Not so hard, but just a new API to maintain. And you'd probably use a library or something because people made it. You can read more about it in my blog. I wrote a lot about it, or just Google it. You'll see a lot of things about object pool. Our next stop is the bus, or actually the connection between the memory and the CPU. Okay, we're going to talk about both. So this is a caricature of how a computer works. So we send commands to the CPU. Okay, the CPU needs data, so it asks the bus to bring it data from the memory. The bus goes to the memory, asks for the data, brings it to the CPU, and so on and so on. The problem is this. CPU got much faster, but memory not so. Okay, for various reasons, we'll mention a few of them later. But what happens is that while the CPU is asking for data from the memory, it just sits idle. And game developers don't like it when the CPU sits idle. They need this. They need to like every piece of performance from the machine. So for this, cache was invented. Okay, cache memory in the CPU. This is another caricature. There are actually several layers of cache, but the idea is that when the bus goes to the memory, it doesn't bring only the memory the CPU asked for, it also brings a bit from the sides. Okay, and it works with the heuristic that if you are using some memory, you'll probably need memory that is close by. The problem with that is that we sometimes have a cache miss. Okay, and a cache miss is this. We need this data for the current task the CPU is handling, but our cache limit is here. Okay, so we missed. This is where the cache missed. So the CPU works on this data, it gets here, and then it needs to ask the data again, so we save nothing. It might ask, why should you care? Right? As I put a JavaScript developer, but it relates to everyone. Can you read that? Who sympathizes with that? So here we come to the climate crisis and how it connects. So there is this equation, okay? The amount of power our computers need is actually the amount of data, or the bit rate, times the distance it needs to move. You divide it with the size of the microchip, or forgot how to call it, the circuit. Okay, so we want small circuits because it's expensive and we want our computers to be small and stuff like that. The distance, we want it to be as small as possible. So the thing is that to bring data from the external memory to the CPU is costly not just in time, but also in power. And by power, I mean this might happen. Okay. Did any of you get your computers heat up when you played games or ran really? Yeah, some of you did. Sometimes it just turned themselves on, which is, I don't know if it's worse or not, because then the fan turns off, and that might be really bad for the laptop. But we don't want to heat up our computers. We don't want to consume more power, because then, yes, one computer is not that much of a problem, but there are a lot of computers in the world, trust me, a lot of computers. And if you develop software that gets to a lot of machines, either a computer, mobile phone, whatever, and you don't optimize it in some way, it consumes a lot of power. Climate change, really bad. But if you don't care about climate, then there are performance considerations. In this case, I did something like that. This is the linear case where you just go over the array like 0, 1, 2, 3, etc. And in the mixed case, you go over the array like 0, 100, 200, 300, then until you finish, then 1, 101, 201, and so on. Okay, so you actually handle pieces of data that are farther away in memory. And this causes a lot of cache misses. And you can see that it's much slower, even in a language that is very high level as JavaScript. So, so you should be very aware of that performance-wise. Let's see. The solution for that is to actually bunch your data together. Okay, it's called data locality. That's the design pattern. How does it work? Let's see. So I click that. Let's see. So this is what I call linear. The non-local is what I called mixed. So you can see it's like 10 times slower. And this is one of the implementations of data locality. Okay, in essence, what was done here is this. Let's see. I created a new array and just set the, sorry, let's see, it's clearer here. If this is the original array, the linear one, so I created a new array where the elements are set like this. Okay, now when I ran the mixed algorithm, so it ran like this, 0, 1, 2, and was as fast as the original one, the linear algorithm. So this is not surprising, but how does this, how would you call this action, moving from this to, from the top one to the bottom one? It has a name. You use it a lot in interviews. Sorting. Okay, this is sorting, and this is the way to do data locality. You just sort your data to be close in memory. So this is pretty extreme, of course. Yes, but let's see another use case for it in the cloud. Anyone uses Hadoop? 1, 2, okay. Pretty niche, but in Hadoop you have MapReduce. Have you used it? Yeah. What happens in Hadoop? In MapReduce, let's say you started here, but you use MapReduce in every node because it's faster to actually process your data closer to where it is than sending it over the network. Okay, it's the same, the exact same consideration. And we also saw that the more data you send over the network, you need more power to move the data. Things warm up, climate change, real bad. So, data locality, when to use? We want to save the Earth again. And when you have data that is processed a lot together, okay, and it's far away in memory, and you want to keep it close in memory, or as we saw in the cloud, you don't want to waste bandwidth or time on bandwidth when you process the data. The cons are also pretty obvious. You need to constantly sort the data according to position in memory or position in your databases, which is not so easy. But if performance is your thing, that you do it. You can see the live example here, and I've written a few blog posts about it, which you can check out. Our last stop would be the GPU, and we'll see how it relates to saving even more bandwidth in our apps. So we have these pictures. Can anyone tell from the pictures what the problem is? You can guess. No? Okay. The problem is repeating scenery. Okay, see the trees here? They're kind of the same. They repeat themselves, but different distances or maybe different branching and stuff like that. And here the fans, they look kind of the same, but different shirt color, maybe different scarf, different hair, different position, of course. So again, we go back to that each fan is a class, is an object of a class, and we can represent it like this. Just give all the details we need, and then we have lots of persons. So when a game developer does that, what the computer does, it sends it to the GPU, this amount of data. The problem is, again, is that you move data, and it's expensive. And especially when the problem is that the CPU is fast, the GPU is fast, but there's a bottleneck when you move the data inside. So I want it to be optimized. So the solution is to divide your data into extrinsic, which is the unique properties of each fan in this case, and the intrinsic, the things that are the things that are similar for each fan. Okay, and then you get something like this. You get flyweight persons and single person model to send. Okay, you save a lot on the bandwidth to the GPU in case of gaming. We actually used it in real life in an app we built where we showed search results from various search engines. So we had a lot of results, as you can imagine. So we had to try to save and optimize this, both for bandwidth and both for actually the actual user machine memory. So we had like extrinsic and intrinsic models here. We don't have much time for code, methinks, but okay, so let's see if we have. So this is an example for the flyweight, an implementation for flyweight. So the same data took like around 14 kilobytes. So you might say it's only 14 kilobyte. But again, try to scale it for your applications. Your applications probably have tons of microservices talking to each other, tons of requests sent from clients to clients. Okay, so take this 14 kilobyte and expand it. Probably your data is much more complex than this simple example I did. So you can save a lot of bandwidth and of course save the earth. Okay, the power is yours in this case. So when to use the flyweight? It's when you have, of course, extrinsic and intrinsic properties in your data. You have a big data set, and you can actually extract the extrinsic properties, or sorry, the intrinsic properties to one model and just send it instead of sending the data replicated. The pros and cons of this, of course, the pros are you send much less data and you get performance, but the cons are that you need to build a mechanism for it. Again, like with everything. So do see if you really need it. And of course, you can read more about it. I think I've written about a use case we did in a real startup for this. Okay, so I hope you now have motivation for learning design patterns if you didn't have so far, but according to the short survey I did, you do believe in design patterns, so it's good. Many people don't, which was quite surprising for me. I can't stress enough the importance of monitoring. I showed you how I do it in JavaScript. You probably know how to do it in every language you're using, but it's super important when you talk about optimization. Okay, you can't just optimize, go blindly optimizing your app. You might not need it. Remember, you have cons and pros for every design pattern, and these design patterns are not like magic bullets. You just don't use object pool for every array you create. Suggested read, Game Programming Patterns. It's an old book. I don't remember what year, but it's really funny, and it's written in Java, actually. So you might actually enjoy it. But yeah, it's a really good one. It's old. The author told me it's outdated, but I don't know. I think design patterns are currently very, as I've shown you in my demos, they still work and they still help with a lot of things. That's my blog. I write a lot about performance and testing, those of you who are into it. And another thing you need to remember is that in the Bible, they even talked about design patterns, so don't use singleton. Actually, you can use it if you need it. These are the links, and thank you for listening. If you have any questions, we have time. So the question was about the dirty flag. Was Cesium.js responsible for the dirty flag or me? Yeah, that was my responsibility. It's not built into the system. Now I think they have something like that, but back then when I worked on it, they didn't. Yeah, exactly. I had to make sure that that the dirty flag worked. Anymore? Cool. If no other questions, thank you very much. I'll be at the Vonage booth if you want to talk about design patterns optimization, gaming, or neuroscience. So yeah, see you later. Cheers.